Hey, quick one today. Let's just do some math. This is going to be one of those mathy ones, but I promise it's going to be quick. We're going to check out the horizon tube test. This is a test being suggested by Antonio Subirats, who's a flat earth YouTuber. He suggests we just take some sort of tube here and we mount it such that it is aimed at the horizon. And he suggests that if one end is aimed at the horizon of a sphere, then the other end will be aimed up at the sky. This is a really good test. It's cool. He thinks, as many flat earthers do, that if the Earth is flat, that the horizon would rise to eye level on both sides. So he suggests this test. So let's test it out. Here's Bobby Shafto giving it a try. Check out his video. And here's Critical Think doing it. Take a look at his video. Always a lot of fun. So what am I contributing here? I just wanted to do the math on this and see, because these results that we got, particularly the Critical Think ones, show really dramatic results, and they seem hard to believe. So let's just take a look at what's the math behind this. Thought I could help these guys out a little by doing the math for them so they don't have to do it. So here we are. Here's our diagram of the Earth as a round sphere. Here's the center of the Earth. And then up somewhere above the top, above the surface of the Earth, we have our observer who's going to look out at the horizon. So there's our line of sight to the horizon and its tangent right there. Okay, obviously not to scale. This is exaggerated for the diagram so that we can work the math. The math will be correct. Okay, here's the radius of the Earth, and here's the height above the surface to the observer's point. We'll be looking for this angle alpha. All right, so here we have our situation where we have a circle for the cross section of the Earth, and we have a straight line for our line of sight. And right here is where the two intersect. The line and the circle intersect at exactly one tangent point right there, and we're going to solve for that. We'll start with the equation of a circle, x squared plus y squared equals r squared, which it's very simple because I just put the origin of our coordinate system right there at the center of the Earth so that I'd get this nice simple equation for a circle. The equation for line, we'll probably remember because it's been drilled into our heads, is y equals mx plus b. So there's our line right there. And what is m is the slope and b is the y-intercept. What is the y-intercept? That's this point right there, which is r plus h. So let's plug that in. Okay, and we want the intersection. We want the intersection of these two equations is when they are both true. So we'll do simultaneous equations, which we learned back in algebra class. Here we go. This equation has y squared. So I'm just going to square this one to make it conveniently the same. And let's expand that. Okay, got this. So now what I'm going to do is substitute this y squared in for that y squared, because that's simultaneous equations. Both of these equations must be true at this particular value of x and y. So we'll take the y we got from the line and stick it into the y we want for the circle and see if we can solve for an x that'll give us that. Okay, that gives us this. Okay, we now have an equation that involves x. Let's solve it for x. We're going to need to get the x squareds together and then the x terms together and then all the stuff left that doesn't have any x's in it. That's right there. You'll probably recognize the quadratic form now. This is a x squared plus b x plus c equals 0. And that's convenient because then we can use the quadratic formula on. Here we have it again. And let's use the quadratic formula. Boom. You'll probably remember that's another one of those that was drilled into you. Here it is. And the interesting thing we're going to find here is this plus and minus. What we have is the solution for the x where the line and the circle intersect. But because we have a plus minus, that means we actually have two solutions. We have two solutions. Why? What? Wait, we're only supposed to have one. Two solutions because depending on what we choose for m, we're going to get different answers. We have m in here. M is going to affect the answers. And if we have an m that shoots down like this through the earth, we're going to get one solution, boom, right there, and then another one when the line exits on the other side. So we don't want two solutions. We want only one. We want one exact solution, and that happens at the tangent. How do we make this equation give us only one answer? And it's simple. Just get rid of this plus or minus by turning the radical part into 0. So what we have to do to make it tangent is to make that radical part 0. All right, this is beautiful. This gives us an equation which has in it r's and h's, which are known constants, and m, which is the big unknown. Let's solve this for m. We'll rearrange and rearrange, and here we have all the stuff with m in it on the left and all the stuff with no m on the right. And that'll give us this. So m squared is this mess that involves r and h and no unknowns. This is now a constant. Let's solve that for m, and we'll get that. Every time we do a square root, remember to do the plus and minus. Why do we do that? There are actually two answers for m. One is this one that I've shown here, which is going to be a negative value. It's going to be looking the sloping downward. But there's also a positive value. A positive value would shoot up like this, right? But it would also go back here and touch the circle on a tangent right there. So we have two values, the plus and the minus. We'll be careful not to get confused by that. So if we have our slope, and we're going to want the minus one. We have our slope, and remember what slope is. Slope is rise over run. I'm drawing the rise as a negative value here. So slope is rise over run, and the thing we actually wanted was this angle here that I called alpha. The thing we might remember about that is that the tangent of alpha is the opposite over the adjacent, and so alpha is the arctangent of opposite over adjacent. This equation here is this one there, so we'll substitute. And there we go. And, I just put the positive here. We'll understand that a positive number now then must mean that I'm looking down. So, maybe put the negative. You decide, positive or the negative. You can define it either way. But there you go. This is the angle. So now let's use this formula to check out what we get for situations similar to what critical think did, and see how he did. So I just threw this into a spreadsheet, just take the height in there, and there's the formulas that I showed you on the previous slides, working out and getting you the angle in degrees. And here's a prettier version of that, and I just increased the height. There's the meters height, and there's the feet height for those of us who speak feet here in America. And I went all the way up to 32,800 feet, which might be interesting if you're going to ask yourself, hey, if I'm in an airplane, does the horizon rise to eye level? Well, according to this, the horizon is expected to be 3.2 degrees below eye level if you're up at altitude in an airplane. So maybe check that out with the Theodolite app on your phone next time you take a flight. See if it's really true. But for this discussion, we were interested in critical think's observation, and Antonio originally thought it would be at 117 meters, but no, it was actually at 97 meters. And according to our calculations, that should be about 0.316 degrees. So that's the angle between the horizon and the horizontal. So down from the horizontal, you have to look down 0.316 degrees according to the globulists, according to the globe model. So that was a lot of math I did, so I thought I'd go check Metabunk, see if they have the same answer. And for a 97 meter viewer height, I get, woohoo, 0.316 degrees. So we are in agreement on that. That's good news. So then let's take a look. The question then becomes, do you think that is 0.316 degrees above the horizontal there? And really it looks like a lot more than that. But wait, we forgot something. We forgot that if you were looking down to the horizon, and that's 0.3 degrees, then the opposite side, looking up, you're looking up by 0.3 degrees up above the horizontal, and the horizon is actually down below the horizontal. By how much, you ask? Well, of course, by 0.3 degrees. So if our alpha angle is 0.316, then this, from the water line, the horizon, up to where the center of the tube is now pointed, that should be, according to the globe model, 0.6 degrees, 0.632. And you say, well, how can I tell? I still can't tell how many degrees I'm looking at. To give it a sense of scale, let's draw out at the horizon point a vertical line and say, how tall would an object be if I was just looking at the top of that object and that object was sitting on the horizon at that distance? We'll call that V, and it just works out to about 388 meters. So do you think we are looking at something 388 meters above the water? Does that seem believable? You know, without any kind of reference, it's still kind of hard to say. But I'm starting to say this falls into the realm of believability. But Critical Think actually went back and checked it for us. And what did he get? Take a look. He put a digital level on top of his rig. And what did he get? 0.3. And our number, 0.316. So kudos, Critical Think. You win. This is pretty much done deal. There you have it.